Um, so let's get started, everyone. So thanks for making it in. Those who made it in person. So I know it was a bit snowy this morning. And yeah, ours quite as many people, and it's a little bit snowy here. That's why there was no sound on Zoom for a few minutes. So today we are going to continue. So let's get started, everyone. So thanks for making it in. Those who made it in person. So I know it's a bit
feedback.
snowy this.
Okay.
Great. Okay, so we're going to continue to talk about classification. And indeed, we're going to still talk about linear classification. So in the next lecture, we'll talk about how to do extend the ideas we talked about last week, and then today to nonlinear classification, but we're still doing linear classification, and we're going to talk about what's called the Perceptron algorithm. So this algorithm is older than the way we talked about it. So last week we talked about how you have a bunch of points and you define some loss function that was not necessarily the squared error loss function, but it was a loss function, and then you ran gradient descent. That's how most stuff runs, but the Perceptron algorithm is kind of an older algorithm that works under slightly different principles, and also gives insight into kind of why classification works, and a slightly different way. So we'll kind of see this today. The Perceptron that we'll talk about, there's a common way to interpret what deep learning is doing with neural nets, and that it encodes a bunch of these perceptrons and kind of glues them all together in some way. So that's another reason why it's important to understand this algorithm. It'll also be mostly by first principles. We won't have this kind of abstract formulation we'll map everything to and say gradient descent is gonna just kind of solve this by magic. We'll actually kind of see why it's working. Okay. Let's look at the schedule. Yeah, if you haven't seen the day is Science Day. If you haven't seen that yet, I encourage you to sign up. We're talking about the Perceptron algorithm. The next one we'll talk about kernels and in general SVMs, which will tell us how to do the nonlinear versions of these things. And then we'll talk about a variety of other kind of classification techniques in the last lecture. And then the final lecture of the semester will be a review. Important thing, quiz 6 is going to be in class on Thursday. That will cover all of clustering, which was 3 lectures, and the first 2 lectures on classification. So just the linear classification, the one last week and the one today. Okay, so don't forget about that. Homework 5 is also out. That's basically due at the end of the semester. Don't wait till the last minute, but it shouldn't be as typically it shouldn't be as much work as homeworks 3 and 4. We're still grading homework 4. Remember, we extended the deadline a little bit, and then there was Thanksgiving break, and that was Thanksgiving for the TAs as well. So they are actively grading it. There was some sort of glitch in Canvas that caused it to reveal the grades partially graded. Just hold on, we're still working on stuff. If I think we fixed it. Can you still see the grades, or is it you can still see it? Okay, well, you're gonna see a little bit how the sausage is made, but just kind of hold on. So someone touched something. I think we know what happened, but I guess haven't been able to fix it. So just kind of bear with us a little bit on that. Okay. So great. So this is so where we are in the schedule. The perceptron algorithm. All right. So remember, we're looking at linear classification. Okay, and so the input here is going to be, again, our set X, so comma Y, and this is going to be in, or is a subset of R D, so the points in X are D-dimensional vectors, cross, so the Y values are in -1 and +1. So we're given a bunch of data points. So one data point. Okay, check my connections a bit. All right, is xi, so yi, right? And so remember, this guy is this is a vector in RD, and that yi is the label. So this is the the label, and there are two classes, and we're going to label them so +1 and so -1. You could label them anything. You could lose them, win, lose. You know, if someone buys a product or not. But we're going to label them +1 and -1, and that's going to allow for a convenient form to think about. So the classifier, the output, right, is going to be a linear classifier. Okay, and that's going to be parameterized by W and B, and these are going to be in RD. So across R, so B is going to be the offset, W is going to be the normal vector. I'll draw a picture of this in a second. But so this is going to give us a function, GWB, which we're going to apply to X. Okay, and this will be in the form of B plus the dot product of W dot, so W and X. So it's a linear function of X, because we're just taking the dot product and doing an offset. Okay, and so this is the form of the linear function, and so then we're going to guess that X is going to map to +1 if G of WB of X is greater than 0, and maps to -1 if G of WB of X is going to be less than 0. We're going to use this as a threshold function at 0. Okay, and so again, okay, so here's the picture I promised. Right, we'll draw more versions of this picture later. Okay, but you have points. These are the locations of your points, X's, and then the labels are minus or plus ones. And then you're going to kind of infer this classifier, which will be represented the decision boundary, where it switches from a plus to a minus value, will be determined by so always a line. So linear classifier in 2D gives a line, but it's really a separator. It's a hyperplane, a D-1 dimensional plane in higher dimensions. And the normal direction of this is controlled by, so W, and B controls this, so the offset. So if you have the origin someplace, then the, let's draw it over here, right? Then the distance in the normal direction from the origin is B. All right, it might not be so like minus B. So this, it's negative, so this is going to be the negative value of B is this length, but it could be positive or so it could be negative, right? So this is how we parameterize this classifier. And so this is our output, and our goal is to learn a W and B, which does a good job on new data that we haven't seen yet, right? Okay, so last week what we did is we said, okay, we're going to measure a penalty on each point on how well it's classified or misclassified or not. In this case, all the points are classified correctly, but if you have a another negative point that's over here, right? So now this point is misclassified, and there's going to be some sort of error, which is kind of the distance to this line, this hyperplane, and that tells you how far it's misclassified. And the more it's misclassified, you get, so like more error is the intuition. And we described a loss function, which kind of became convex, and then we could measure this at all the points, and we could optimize this values for W and B, right? So this was what we talked about so last week. We're going to be talking about a different algorithm, the Perceptron algorithm, that is not going to go through that framework. And so it's going to need to work on a simpler version of the problem. Okay, so the Perceptron algorithm won't always work. You need to handle 3 conditions to use the Perceptron algorithm. 2 of those conditions are so benign. That means you can get rid of those conditions by transforming the data. The third one is going to be one that the algorithm's not going to work if it does not so satisfy this condition. So it's not always going to work. Okay, so before we talk about the Perceptron, we need to talk about simplification. Perceptron, Perceptron. Okay. Okay, we're going to need to assume 3 things about the data. Okay, so the first one is we're going to assume that the decision boundary passes through the origin. Okay, so what does this mean? It means if you draw a picture and you have minus points over here, and you have plus points over here, that we're going to find a decision boundary that passes through the origin. Okay, whatever classifier we learn is going to need to pass through the origin. In this case, it's fine. It can do this. Basically, mathematically, what that means is that the offset value B is going to be 0. Okay. Okay. So this isn't a big deal. It just means that we're actually solving for GW of X, which is just X. And the offset, you add the B offset, that was adding a 0. So you just ignore that. You can't solve for that. Okay. So this isn't, again, this is not really a problem because I can convert kind of X to 1X, right? So now this is in RD, and I can convert WB or BW, right, into alpha 0, alpha 1 up to alpha D, and this is alpha, sorry, this is D plus 1, and this is alpha is also in D plus 1. Okay, so now if I just learn this alpha parameter, this d plus one dimensional vector, like we did with linear regression, it's now just a dot product. Okay, so kind of this is a cool picture. You can think of this geometrically, kind of what's going on. Let's say this is the d-dimensional space. I've got, so this is 0, and I've kind of put, I put all the data points that used to live, right? So I've got my minus data points here and the plus data points here. And I can't really get the separating spot to go through the origin, which is supposed to be over here. Okay, but if instead I say, well, I'm going to put all these up so they have, right, so they have an extra coordinate, which is 1. Okay, then what I can do is I can say, well, now I want the linear classifier to go through here somehow, and so I can always draw it so it goes through the origin. Okay, so I can always do this. I can always lift them up, and then I can always draw it so it goes through the origin and it intersects at some spot. Okay, this has slightly changed the geometry of the problem. Now I'm measuring kind of the distance to how well the classifier is at this kind of this small angle. So it's a little bit different, but it is basically the same problem. Okay, so people will do this transformation all the time and not really worry about it. Okay, so we're going to assume this transformation has been done, and we're just going to solve. So we're just going to solve kind of this problem. Okay, assuming this transformation has been done, and kind of ignore this aspect of it. I've slightly changed the notion of what it means to be, how far I am from the classification bound. Okay, okay. In general, you recommended not to kind of, if you don't have to do this, you generally don't do it. You often keep around this offset or this bias term. It's useful in some ways, but in this case, we're just going to assume this has been done. Okay, so this is the first, so simplification. So number 2, we're going to assume that for all data points xi in our data set, that the norm of these data points is less than or equal to 1. Okay, so this again, this is not strictly necessary. This will be useful. We're actually going to do a little bit of analysis of why the algorithm works, and it's much cleaner to think in this sort of setting where all the data points have a distance less than 1. It'll simplify our calculations. You can always kind of think about, yeah, so let me draw this bigger. You can always think about, I've got some, so some negative points. I assume I've already done the first transformation, and that there exists a classifier that goes through the origin, and that's the one I'm going to want. And I'm going to assume that there exists some unit ball, centered around the origin, right? So this length is going to be 1, and all the points are then going to be inside this ball. Okay, so I'm just going to assume this, and this will simplify some calculations. Sometimes this is true by construction of your data, it turns out. For instance, if you are doing like a kernel method, which we'll see on Thursday, if you're doing a kernel method and you do a transformation with your data, the kernel sometimes guarantees the new representation has a norm of at most 1. So sometimes you can have this by guarantee. Sometimes you take your largest distance from the origin. I can take this largest say, distance here, right? Say, okay, or maybe there was some point here, right, that was distance exactly 1. Well, what I actually did is I took this point xi, and this was the max, and I said, well, I'm going to divide everything. So say that we'll call this x max, and for all xj, I'm going to set to xj divided by the norm of x max, and this will just divide all the coordinates by this value, and then I have the result of this is going to be that the norm of all the points is going to be at most 1. So I can always transform this, right? Okay, so this is also pretty easy to do. Yeah.
If we transform it and then put some model, does that mean that something we
So yes, actually no. What's going to happen is your classifier, you're ultimately going to draw a classifier, let's say one that goes through the origin. Remember, we already did this first transformation. And this classifier, all I need to represent it is going to be some normal vector, which will also have a norm of 1. So it's going to be length 1 here, right? And all I do is I take the dot product with the normal vector. If the dot product is positive, I classify it positive. If it's negative, I classify it's negative. So all this is doing is changing the length of that value, but not its sign. So it turns out this transformation, I'm not going to really need to worry about. If I care about the real distance from the classifier boundary, then I need to pay attention about that. And in some cases you do, but not for things we'll talk about in this class. Sometimes the further it is from the boundary, the more confident you are in that classification. Where the closer it is to the boundary, you have less confidence, and sometimes you want to use this. In fact, the loss functions we talked about last week somehow are encoding that information. But in this case, we aren't going to be looking at that. So you don't need to worry about this transformation. Yeah. So good question, though. Okay, great. So this is the second one. The third one is, and this one is not always true, is that you assume that there exists a perfect classifier. Okay, the perfect classifier is one that let's call this so W star. Okay, so that for all x, y, right, in our data, that G of W star of x, the sign of this is equal to to yi. Okay, so there exists a classifier that will classify everything so correctly here. Okay, so and that's what's shown in this picture. In this picture, I've classified everything correctly. If I'm in 2 dimensions and I have a positive point up here, there does not exist a perfect classifier if I go through the origin. There's no way to have a linear classifier that has all the plus points separated, linearly separated from all the minus points now, right? That plus point up here, this is a violation of condition 3. Okay, so this this violates so this violates the third assumption. Okay, so I can't linear classify that point from the other point. So if this was my input data and I run the perceptron algorithm, it's not going to work. Well, so see why that is. Okay, but it's so right. So yeah, so how strong is this assumption that I have to that I have to assume the data is going to be so linearly, so is going to be linearly so classified, that I can do this with no error. If I'm in two dimensions, this is probably a pretty strong assumption. So in fact, when people were first looking at neural nets, well, not the first time, I guess there were like 3 rounds of times in machine learning that people were like looking at neural nets. First, when the perceptron was invented in like the 50s, this was kind of how people were thinking of classification. Then I think it was like the 80s, there was a lot of work where people were getting excited about like neural nets, which are, or things like the perceptron kind of algorithm we're going to be talking about. They were showing it could generalize to new data and some cool stuff. And then, one of the realizations why people stopped working on it was kind of claimed to be the discovery, well, linear classifiers, when you think of it this way, this wasn't initially the picture they were always drawing, thinking about it. But if you think about it this way, it can't classify properly here. A linear classifier cannot properly work with this sort of setting. Probably more the issue was they didn't have a lot of compute resources or large, interesting data sets back then. So that was probably more of the issue. But so I mean, this is kind of like a real challenge. If I'm just building a linear classifier, I cannot handle this setting and find a perfect classifier that's going to generalize for all points. If I want to find the right model for this data, this is not it, unless you assume, well, there's some data with noise, right? That sometimes some fraction of the data is mislabeled, and that's okay. Well, then the gradient descent form with the loss function, okay, maybe I find this classifier, or maybe it's shifted a little bit towards the blue points. But if it goes through the origin, maybe this is the best classifier, and I'm okay to live with some noise. I'm okay if 1/8 of my predictions are actually incorrect. And maybe I assume, okay, there's noise and that's why it's incorrect. That's probably a fair view of it, but the algorithm we'll talk about, the perceptron, won't be able to handle this case. Okay, this is in 2 dimensions. Okay, a lot of times when you're using a linear classifier, you might want to work with much higher dimensional space. In higher dimensions, this is less likely to happen. I have a lot more freedom in how to design the linear classifier. And in fact, if the number of points I have is less than the number of dimensions, then I can always find a perfect classifier. Okay, if n is less than d, right, I can always find a perfect classifier. I have a lot of parameters I can choose, fewer than the number of data points, and it turns out I can always do it. And in practice, if n is, say within a factor of 20 of d, you can often find linear classifiers still, as long as the dimensions are high. Most data, if you're trying to find some linear classifiers in say 100 or 300 dimensional space, and there is a real pattern, then those will probably structure, and then you'll have enough degrees of freedom left over to try and find a one that doesn't misclassify any of the points. So in high dimensions, this is typically not always a problem. It could be still, but it's not always a problem. And we'll see with the kernel approaches we'll talk about on Thursday, you basically transform this into a situation where, again, you can always find a linear, or you can always find a classifier. It'll be a kernel classifier, but it'll use the same algorithm, and you can guarantee you can always find a classifier in that set. Okay, so this is an issue, but it's not always an issue. Okay, so you do need to pay attention to this, but it's not means this algorithm we should ignore it because it can't handle this case. There are plenty of cases where it's So it's still going to be useful. So, yes, okay. What we're going to, so let me tell you what the algorithm is now. The perceptron, so algorithm, okay? It's going to be, again, like all the algorithms in this class, it's going to be pretty simple. So this one you could actually implement, but I'm not going to ask you to implement it in the class, but you may have to think about it. So still you should, so pay attention. So 0, we need to initialize, okay, it's going to be an algorithm that's going to iterate again, not exactly gradient descent, but kind of like that. And it's going to set W equals yi times xi for any xi, yi in the input. Okay, so I can take any data point, and I'm going to write down the normal direction W. So my parameters, right, as the sign times the vector value of any of the data points. Okay, so this should be a little strange. There's this cool trick that's going on right here, right? This is going to be a vector in RD, right? And I'm going to somehow use this trick that the representation of my parameter space, W, right, this normal direction, is the same object as a vector of a point, xi. So if you're taking a class in physics, they probably will tell you not to do this because Wi is really a vector and xi is a point. And those are kind of, in physics, those are fundamentally different objects. In computer science, they're both arrays, so it's fine. So it's okay to do this, and this is what makes the algorithm work. Okay, so the fact that the data points and the parameters are both d-dimensional arrays. So there's kind of a real interesting trick that's going on here, and we'll kind of see this more as I write down the rest of the algorithm. Okay. Okay. The rest of it is just going to repeat some updates. Okay, I'm going to say for any xi, so yi in xy, such that yi xi w is less than 0. So this means it's classified. Okay, so I've done this trick again where I've written the function g of w, right? Remember, this is g of w of xi, and I've multiplied it by the sign. And so if the signs match, right, I should have something that's positive. If they don't match, that means they're misclassified. I'm guessing the wrong sign. Then it's going to be negative, and it treats both cases the same way. If it's a negative or a positive, it's going to, if it mismatches, it's less than 0. So this determines if a point is misclassified. So I'm going to find any point that's misclassified. Okay, find any point that's misclassified, and then I'm going to do an update. I'm going to do W. My classifier is going to get W plus yi times xi. Okay, so again, I'm kind of abusing this representation of a vector and a point, but they're both d-dimensional arrays, so I can add them together and get back another d-dimensional array. Okay. All right, and so that's the whole algorithm. Okay, until no points, so misclassified. Okay, so again, if there was not a perfect linear separator, then I can't end this because I would never have no points misclassified. I would keep updating, forever. You could say, or say t steps. I could set some upper bound on the number of steps, and we'll see actually we can get a bound on how large t will actually need to be. It's not going to be so too large. We aren't going to need that many steps. But in principle, you eventually want to find a classifier which does it has no misclassified points. Okay, yeah. There's a question I just missed. Does this only work in the modern age of computers, or could this work in the 1800s? Okay, 1800s. Yeah, let's see. There was in the the first learning machine was built with gears. I think it was for playing chess or something. Was it? Maybe it was check. It was some, but it was. If you're talking about 1800s, you're talking about gears. It's before we had vacuum tubes. This worked on vacuum tubes sort of stuff. It's pretty simple algorithm. Maybe not in high dimensions. You have to, big high dimensional arrays probably would, be bigger than the size of these computers. Yeah. So I don't know if this worked in the 1800s, but this definitely you could write this pretty simply. It's a pretty simple algorithm here. So there's a question online about this for any, right? So you could choose any misclassified point. So in principle, what you would do, I want to write one more step of the algorithm. So you would return W gets W divided by the norm of W. So this makes it so it's a unit vector at the end. You kind of build up a longer vector that will go, our analysis will use the fact the vector gets longer and longer, but then you often want a vector, so it's a unit vector. Okay. Yeah, so this, for any point, okay, so in practice, I may need to search over all the points, whether it's in any point or not. But what I would typically do, I would order all the points, and like incremental gradient descent, I would just iterate over them in order, and I would kind of keep track of the index of the last point I had to update. And if I get back to that point, I know I can stop. Right? So you don't search from the start of the array every time. You go through the list of points, and when you get to the end, then you go to the beginning again. Okay. In principle, you might need to make t steps, and each step you might need to look through all the points. Maybe only one point is misclassified. You have to look through almost all of them. But in practice, you usually go through the list of all points once or twice, or maybe you don't even make it through all the points before you've done enough steps and you can stop or something like that. But you probably need to make it through at least once to check everything is misclassified. Okay. But it's really any point. There's a version of this algorithm where you always choose the most misclassified point, and that point, you can have slightly stronger guarantees on that algorithm. You'll be able to guarantee that it not just finds a good classifier, but a nearly best good classifier. But we won't so worry too much about that. All right. Okay. All right, so maybe this is a good time for a break. After the break, I'm going to talk about an important concept which could show up on your quiz, for instance, called the margin, which is how you think about how well this is working, and then we'll use the margin to see how many steps you actually need to take. But we'll take a break for like 3 minutes, and then we'll come back. Yeah, but you can ask me more questions about the 1800s over Zoom at this point. So yeah.
Just wanted to ask, when you say for any point, is that synonymous for through a bunch of points and the first one that makes the requirement?
That's typically how you would implement.
So it doesn't need to be random.
It does not need to be. It does not need to be random. Yeah, in fact, it's not. There's nothing in the analysis that is random at this point. You will we will assume analysis that will have a little random stuff. You need to start with the random. Oh no, there's nothing random about this algorithm. Yeah, it's completely so deterministic algorithm.
I don't know how you prove that in your head, but I assume, and we'll go there now.
Oh yeah. We'll go through it. Yeah, but you can see I didn't make any random choices here. So this will work. It will find a perfect classifier if one exists, and we'll see that.
Yeah. This case, could we just shrink our circle to exclude that plus and have it be okay?
Oh, and have it be like an outlier?
Yeah, just, could we just be like ignore that one, or
but how do you know which one to ignore?
can we just like shrink our circle until we get a classifier that works?
Yeah, you could try doing that. But at this point, might be actually mixed in like the convex hull of those points. It could be harder. Yeah.
But like in a simple case like this, is that something that we could do, or is that just?
I mean, you could do it. I don't think there's necessarily a lot of rationale behind it. Some of those, I mean, there might be other ways to try and find dealing with outliers in data. How do you decide which point is an outlier and which is an inlier? Yeah, so in here you would, let's see, there's, I would probably run the perceptron algorithm, and if there's one point that keeps getting called over and over again, you might say, well, let's see if I remove that point and then rerun the algorithm again.
Would that be useful, or would we be like, we still have to take that point exists, we can't classify it?
Yeah, but like, it's reasonable to assume that there's some outliers in your data sets, and there's some noise that there's mislabeled data or misread data, and so it got the wrong coordinates, right? This happens, right? Yeah. If you look at there's these common image classification data sets, and the classifiers have gotten so they're huge, right? They've gotten so good. There's points that are consistently misclassified by the best classifiers, and people have gone and looked at those points, and they've been mislabeled. No one realized until they built really good classifiers to do that. So how do you do that here? There is some trick you can do where you always don't take, there's a version of the algorithm where you, instead of taking the most misclassified point, let's say I assume there's k outliers, and I'm going to take the k plus 1 most misclassified points.
Okay.
And if I always run that, then the algorithm will conclude, find a classifier with up to k outliers. So this will actually work.
Oh.
Yeah, we won't cover that in the rest of the lecture. That's kind of piecing together some stuff that's not commonly written down, but that should doing that should work.
Okay.
The issue is this scales with k, the number of outliers, not the fraction of outliers so well.
I was just wondering if you did have an outlier, could you just, we can make the circle smaller.
Yeah, so it's right. The circle being smaller is not necessarily the right way to think about outliers in the setting. The 0 was somewhat artificial, right? So remember, we did this lifting, implicitly, and so there's kind of, that might not really be the furthest point away from. Yeah.
Okay.
Yeah, this is interesting to think about.
Thank you. What was the snow? What was the first assumption for
the first assumption was that the classifier goes to the origin. And so you can do a transformation so that you had one coordinate the same to all the points, and then if the classifiers here, you can have something go through the origin or one dimension. So
Thank you.
okay, sure. So great. So let's get back to it, everyone. So I want to talk about why does the perceptron algorithm work, and in general, have a different way of thinking about how good is a classifier, right? We talked about these loss functions before, and they kind of give you an error, and that was probably a pretty good proxy. There's another kind of more geometric way of thinking about it called the margin, okay? And so let me define the margin, okay? And we're going to have, might as well have a classifier that, well, it doesn't need to go through the origin. We're going to have a bunch of negative points, okay? And we're going to have some positive points here. And we're going to draw a classifier. Let me start, see it, different color here. Let's do purple. Okay, we'll start with this classifier, or this is the decision boundary of a classifier, right? So this is the 0 point of the g function. So this would be g of wb of x equals to 0, right? That's what this represents, okay? And now I want to, margin, okay, is going to be, is the distance to the, we'll say this is, so this is the margin. This is the distance to the closest point to being misclassified, okay? So in particular, we'll write this down as gamma. Gamma is the margin, is going to be equal to the min over x, y in our data set, okay, of the value yi wxi dot plus b, okay? So what is this value for if a yi value is negative, then I'm going to take the right, I'm going to take this normal direction, right? A normal direction dotted with that negative point, right? Is going to give me a value which is negative even with the offset. Okay, even with the offset, the value is going to be negative for the point I've highlighted up here. Okay, this value is going to be negative by multiply it by yi, so it becomes positive. It's correctly misclassified, but what this tells me is the length of the misclassification, right? So this is how far is it misclassified. If I were to compute this value, I'm taking the mean over all points, right? The min value for all points. If I compute this distance to the classifier from another point here, right? This gives me a larger distance. Okay, if you remember, this is underlying function g. This is the 0 set, but it's a linear function that's kind of coming out of the plane and giving positive values for the reds, the positive point where the pluses are, and negative values there. And the slope is 1, right? Because I've normalized w to have a norm 1, that means the slope of it is 1. So the distance I travel in the plane is the change in the function value g of wbx, right? So in general, this is yi times g of wb of xi, right? So I can write this as this function, and it's how far has the function changed, and then multiplying by yi gives me the right sign. So it works the same for negative and positive points. Okay. Okay, and so this is the closest point to the boundary, and the margin is how small is that? So that's my margin for error. So what this is saying is that there is kind of this region in here, okay, where this that I don't have any points close to this, you know, this classifier boundary, okay, within this region, this margin area. The margin is the length, but this kind of defines this kind of slab along the classifier boundary that is kind of a safe region, saying, okay, if there are points with this much error in their location, I still won't misclassify. I could perturb a point a distance of gamma, and it will still be classified the same way it was before. That's what the margin tells me. Okay. So, all right, so do you think it's good to, how do we think about the margin? Do we want a small margin? Do we want a large margin? What do you think sounds good? It's large, yeah. We like a large margin. That means we have a larger margin for error, right? So you want this safe zone to be as big as possible, right? You want that you less likely to misclassify a point if there's noise in the actual reading, right? So that makes it more robust. And remember that our goal is actually to generalize the data we haven't seen yet, right? So the data we haven't seen yet is kind of from some distribution here that we don't know what it is, and probably some points aren't necessarily, say, in the convex hull of these points. They might be outside of it. They might be kind of a little bit outside where the points are, and we don't want this classifier to accidentally chop off some of this unknown sort of distribution. Yeah.
So all the points seem like they're vectors. So they all vectors. So like the margin is that a vector?
No, it's a scalar, right? So if I do a projection, I do the dot product times W. That would give me the location along that vector, but I just want the distance along that vector. So and that's what the dot product is giving. What you're right is that there is an interpretation that if I set, say, W here, and I drew a line through W that should be normal to this classifier, okay? Now I could think of projecting all these points onto here, and this same with the blue points, right? And the one that defines the margin is going to be exactly right where that orange line is going through, right? So this is a good way of thinking about it, right? I project them all onto here, and this one point, right? It's mapped onto here, and this defines the length of the margin now, right? So you could think of it this way, but I'm just measuring the distance, right? So this dot product is only the distance. It's not the actual doing the projection. Yeah. Okay, so I want this margin to be as large as possible. Yeah, and so this picture's got a little bit messy, but has this, maybe I'll draw in here, then I'll draw a fresh one again. Is this the best? You know, I would like to find a classifier that has the largest possible submargin. Do you think there's one that's is going to be better than this one? Yeah, I can kind of see it in this drawing here that if I look at this projection, this closest positive point projects over here, and the closest negative one projects here. So all I could do, I could just shift it a little bit in this direction, and it would move towards here, right? But I could also rotate it. right? So let me try and draw the max, what's called the max margin classifier here. And it will look something like, draw this thicker, right? This would be like the max margin classifier. Okay, and now this is going to have kind of 3 points, which are equidistant. Okay, maybe you think there's a 4th point, but generically in 2D, there are going to be 3, it turns out. 3 points which are equidistant from here. And this one has the margin is larger, right? So this, I would say, this corresponds with GW star B star of X equals to 0. This is the max margin. Okay, so the max, so margin, so separator, okay, is going to be W star, so B star is going to be the arg max over WB in RD cross R, min over XI YI in XY in our data of YI G of WB of XI. Okay, so if you look at just, this one is just to find the margin, right? And I'm finding the maximum choice of the margin of all possible classifiers. So the one that's maximizing this margin, which is the max of the min of all of the data points here. Okay, so again, let me draw a little bit cleaner picture of what's going on here. Right, so I've got some negative points, some positive points. Okay, and then there's the max margin separator. This would be G of W star B star of X equals to 0. That's the separator point where it's the dividing line. And if I compute all of these distances, these 3 would look like they are the so these 3 are called these are called support points, because these support the margin. Okay, and I could draw this line through here, right? That is the safe zone. There are no points within this gamma distance, right? This is gamma equals the min over xi yi of yig w star b w star of x. Okay, so this is, and I'll call this so gamma star. So this is the max margin. Okay, this is the max margin, which is the margin of the max margin separator, and the max margin separator is the one that gives me the largest possible margin, gives me the most margin for error in case there's noise in the data. Okay, and this tells me how good the classifier is. The larger the margin, the better it works. Okay, it turns out it's also going to be the larger the margin, the easier it is to find the classifier. Okay, the perceptron algorithm is actually going to run in fewer steps if the margin is larger. It's going to be easier to find a perfect classifier. If the points, the positive and negative points, are very close to each other, it's going to be very hard to find exactly the right sort of separation between them. Okay, but if they are very well separated, it'll be pretty easy. right? So if I were to just, let's say that the origin, and again, the max margin does not require that the classifier goes to the origin. So let's just say it goes to the origin. And if I were to just pick any one of these points, say any of these red points as my initialization, it would already work. I would stop. It would automatically give me a perfect classifier after just choosing most of the points. If I pick them as the first point, they would just give me a perfect classifier. But as the margin is smaller and smaller, and it's harder to find that perfect classifier, I can't necessarily pick just one of the points. It needs to be some, say, linear combination of the points, right? And so that's, remember, the perceptron algorithm is kind of adding up the contribution of the points, and so it needs to be something in a linear combination, and I might need more steps to actually sort of kind of converge to the, the right value. Okay? Okay, so this margin is going to play into why the perceptron actually works. Okay. Let's go through now and actually, I'm going to run through an example of the perceptron algorithm with the drawing, and then we're going to kind of try and analyze a bit why it works. It turns out it's like it's a 3-line argument, but you need to understand those 3 lines. So it's a pretty simple argument. Okay, so let's go do an example now. All right, where all of our points are within a unit ball. Okay. As we run the algorithm, the W vector might keep getting longer and longer. So that's might go outside the unit ball. So I need to leave a little bit of space here. But all the data points are inside of this unit ball. Okay. And let's draw some points here. Make sure I can build a classifier. Again, if the points are really well separated into 2 clusters, then this is going to be pretty easy. So I've drawn it somewhat tricky. Okay. And okay, so this is my initialization. This is the data. And I'm going to start with an unlucky choice of which point to start with as my W. Probably if I pick this point here, this lower left red one, it would probably, I could probably stop right away, but let's say I picked this point as being W, right? So actually, so if it's negative, right? So I'm actually going to get, so I'm going to think of this point, but I'm going to go take the negative of that vector. So my vector W is actually going to go here. Okay? Right, so, and then that's going to give rise to a normal vector, which is the classifier. And it's going to say everything pointing down in the direction of the vector, right? In the direction of W down here is going to be classified positive, and everything above is going to be classified negative. And I actually did fairly well. There's only 2 misclassified points. Okay, so I initially picked the negative point, and so my W is negative. This is equal to y1 x1. So we'll label this guy as x1. And because y1 was a -1, it's pointing the opposite direction. Okay. Now we'll pick another. Let's say that this point is x2, and it's misclassified, right? If I look at, this red point down here, it's classified correctly. I don't do anything. I have to pick a misclassified point. That plus point is misclassified. So let's pick that one. And what I'm going to do is I'm going to add, right? So this is x2. I can think of it as a vector, and I can add it onto here. Plus x2. Y2 is +1, so I don't do anything. And now this is my updated point W. So this is the normal direction. And let's say maybe we'll save so we have one more step. I'll make it slightly not normal. And so this will be my choice of the classifier. Okay, so now it's done better, right? After one step, my classifier is now looks like this. Okay, and I've now correctly classified 7 of the 8 points, but not all of them. It is not guaranteed to be monotonically increasing how many I misclassify. Okay, but I've done a little bit better. I should probably rotate a little bit further kind of in the direction it's going. Okay, so the only misclassified point that's remaining now is going to be this point over here. We'll call this x3. Okay, and so now I want to add that vector onto W. This is plus y3 x3. So it's actually subtracting x3 because it's the negative. And so now this is going to be my updated W. It's gotten larger, it's going outside the circle, but that's going to be fine. I'm going to get a new classifier here. And okay, we can say at this point we can stop. Okay. Okay, at this point, all the points are classified correctly, right? Good. So there's no more misclassified points. This is you know, after 3 steps, I've so gone to a perfect classifier. All right, so that kind of makes sense how it works. It doesn't always keep going in some directions. It can go back and forth. This vector W is going to grow longer over the case. I guess at the end, I would normalize it so it lies exactly on the disk, but this is basically how it works. Okay, and it's kind of a result is a linear combination of these. The result was I took these 3 points, x1, whereas x2 and x3, and I somehow took a weighted average of those points in order to get this vector out here. And from positive examples, kind of the way this is called like a perceptron, kind of like a neuron in the brain is the idea. When it gets a positive example, it gets longer in the direction of the positive example. If it has a negative example, it misclassified. It says, oh, okay, push me in the back in the other direction. All right, okay, so that's basically how the algorithm works. Okay, let's see why it works now. Okay, why does Perceptron work? Okay, and in fact, we're going to say that it uses at most t, and this is going to be equals 1 over gamma star squared steps. Okay, so again, this is the max margin. So as the max margin gets smaller, right, 1 over that number is going to be larger, and that's that number squared. And the margin is always less than 1 because remember we normalized all the points, right? So this bound somehow is, if we didn't normalize all the points, we somehow need to scale this by the norm, the size of the data. But we've normalized all the points, so the margin is something between 0 and 1. So for instance, if the margin is 0.1, we're going to need at most like 100 steps. That's in the worst case. We need at most 100 steps. It's often much less than that. Okay, like here, the margin here of the max margin, this is not the margin we find. The margin we found is actually pretty small, but the max margin is maybe about 0.1, about 10% of the radius. And that would mean that, but we only needed 3 steps. Okay, so this isn't completely tight, but weird cases might happen. Okay, and this does not depend on the dimension of the data or anything like that. Just depends on the margin. Okay, So in order to bound this, we're going to consider there are basically three steps. The first two steps is we're going to bound two quantities. We're going to bound two quantities. First quantity we're going to bound is W dot W star. So this is the length of the of the normal we found projected onto the max margin. Okay, right? Because the max margin is of length 1. Okay, but W might keep getting longer and longer. So we're going to argue that it's not going to get that we're going to argue, yeah, that this one is not going to get so, or it's going to grow every step. And we're also going to look at the quantity of this, of the length of the margin we find. We're going to say that this is not going to grow so too fast. Okay, so this first one is a little bit easier to see. We're going to say that this is at most. So this is going to be at most. So T. Okay. So we're going to argue that each step it's going to grow by at most 1, right? So we can see that W, if we have W after one step, and we're always going to do WI XI, W plus WI XI. This is the update we do in any one step. Well, you can write this as the old WI. I can just, I can factor stuff out, plus YI squared XI dot XI plus 2YI W XI. Okay. I know that this value, this is always 1, because it's either -1 or +1 squared. And this value is at most 1, because the length of every data point is at most 1. And this value is less than 0. I know I only chose a point that was misclassified. Okay, so this is less than or equal to W plus 1. So if I take T steps, right? If I take T steps, so after lowercase t steps, this is going to be at most T. So I'm going to say that the length of the W I found is less than T after T steps. So the length of that vector I found, remember, it can grow outside the ball, but it can't grow too fast. Okay, it can't grow more than the squared norm cannot grow to more than T after T steps. Okay, okay, so this handled this case here. The other thing I need to do is to say that W dot W star grows larger than T gamma star. So every step, it's going to get, this is essentially saying it's getting closer and closer to what the right answer is. Okay, remember the projection. I've got W star, and this is a unit vector. So the W I find is the projection onto here. It's the length of this projection, and I want this to grow with T. Remember, the first quantity is the squared norm. So this implies that the length of W is less than or equal to square root T. Okay, so I can do a similar analysis here. This is W plus YI XI. This is after one step. W star, I can expand this into W dot W star plus yi xi, so W star. Okay, so this is the quantity that I had before, and then I'm incrementing it by this. What do I know about this quantity? That so if now I'm comparing it to the optimal one, and I know that for the optimal one, the margin is at most gamma, and so this will tell me how much is it misclassified afterwards. Well, it's classified correctly with gamma, with W star with respect to W star, and W star is the optimal. So because the margin is at most gamma star, this is greater than gamma star. This quantity here. So I've increased it by gamma star every step. Because it must be with the perfect classifier, the max margin one must increase with respect to that. It's kind of moving in the right direction. So with this, I can say I can get this quantity here, that it's moving closer, and now I can put these. Those are the two steps. The third part is I'm going to put these together. I'm going to say that T gamma star is going to be less than W star, right, which is the quantity I just proved. This is less than or equal to W. Okay, so if I know the dot product W times some unit vector is always less than W times the unit vector in the same direction. This is the vector which maximizes the dot product with W in the same direction. Okay, and this quantity is exactly equal to the squared norm of W, which I know is less than or equal to square root of T. Okay, and now I can solve for T, right? So now I can put these parts together to say that if I can only take a step if T is less than 1 gamma star. Okay, I know I must increase it if I take more than this many steps. Oh, this is squared. Less than 1 over gamma star squared, right? So I divided both sides by gamma star, divide both sides by square root T, and I squared the quantities, and I can reach this inequality. So if I took more than this many steps, I violate some underlying properties here. I get some contradiction, so it must terminate after this many steps. So terminate after 1 over gamma star squared steps. Okay, so I can set an upper bound in the number of steps that depends only on the margin, independent of the number of data points, independent of the dimension I'm in. It only depends on the margin of how much error is in between these. And this did not, I used the dot product here, but we'll see actually on Thursday that when we get to like these nonlinear approaches, I can replace this with the kernel, and the same proof will go through. So it will only depend on the margin, which is defined on this, or the max margin, which is defined here. So if there exists a good classifier that has a law of margin for error, then this will conclude in a small number of steps that depends only on that, even for much more complicated problems. So this, yeah, so even though it's kind of a simple algorithm, it's not what's kind of, really used anymore. It kind of has a lot of nice properties. And in fact, for very large scale linear regression and very high dimensions, there are libraries built around this which are faster than using kind of gradient descent if you can assume stuff is still going to be separated, which is often true in very high dimensional spaces. So, okay, great. So we will stop here. Remember, the quiz on Thursday will cover up through this lecture. And then we will see how to, we'll also see in lecture on Thursday how to take this algorithm and turn it into a nonlinear algorithm. We'll start with the perceptron, and then we'll go to like the gradient descent version of it. But we'll start here, turn this into nonlinear, and that'll be an easier sort of way of slow transition. All right, great.